Okay, so we talked about the first discovery was X-rays. The second one was accidental by radioactivity by Henri Becquerel. And based on that, Marie Curie and Pierre expanded it further and discovered the radiation phenomenon from pitchblende. So that's well known. And then obviously with the advent of heat, people had figuring it out, because now, as I have mentioned so many times, the most popular, science popularizers are named a British Egyptian physicist named Jim Al-Khalali. He talks about the bicycle lamp as to how it starts out with yellow, and as you pedal faster and faster, the light becomes really bright and white. And the sunlight is also, obviously, it's white and yellowish. It's very rarely blue. It's very hard to reproduce blue. And that has to do with, this was the problem with something called black body catastrophe. And that gave us the idea as to how, the classic theory of light as a wave fell apart. Okay, and that came up with the idea of light comes as quanta, and that made sense with the temperature and frequency. So explains about how, and obviously we talked at length about the most Einstein's paper, the Annus Mirabilis. The first one was photoelectric effect. So based on just one mathematical thought, he explained that yes, light is indeed like a quanta, not just wave. And the second was the most mundane thing called a Brownian motion. And the third one was the famous E equals mc squared. So we talked at length about that. And then moving right along, so this was, and we talked about Henri Becquerel. And then at the same time, Rutherford, who was a New Zealander, was working with cathode rays and came up with the idea of, this was, one can say, golden age of physics. Everybody thought physics was finished, but the first 50 years from 1900 to 1950 were just absolutely golden age. And it made the modern world as we come to know it, because everything that we look around you, like starting from computer to electricity and all this, obviously it dates back to the earlier 19th century of Faraday and Tesla and Edison. Obviously, we give them enough. We spend more time than perhaps we should have, but this was the starting of very relatively simple experiments. Rutherford not only proved that the electrons were already discovered by J.J. Thomson. Rutherford came up with the concept of alpha radiation, which is the helium nucleus basically, and the concept of the nuclear model. A simple experiment as to how the particles were bouncing back on the other side. That just threw out the so-called plum pudding model of the nucleus. Now, obviously, the two people that were totally contradictory. Rutherford was obviously, as they call the colonial and a great experimental. On the other hand, Niels Bohr was rich philosopher, highly theoretical physicist, and these two people gelled together and worked with trying to explain. And it's led to the foundation of what we know as quantum physics or quantum mechanics. And this, one can say that Niels Bohr combined, the chemistry and physics, to explain the, obviously Mendeleev had proposed the periodic table. Okay, proposed the periodic table, but that had to be coincided with the concept of quanta, and so Rutherford combined. Okay, and so this is, and Niels Bohr, the focus of science had shifted between three institutions, type of thing. Cavendish Laboratory in Britain. Niels Bohr, obviously after he won the Nobel Prize, was funded by the Carlsberg industrialist and had formed the Bohr Institute, and he was put Denmark, the little Denmark, on the map of fundamental work on physics. At the same time, I'm sorry, did somebody say anything? Yeah, okay. Okay. All right, yeah, I think I'll just make sure that everybody's, oh yeah, I think everybody's muted, thank you. Okay, and and the third thing was that Germany had, had industrialized the Industrial Revolution, and had funded, what was known at that time Kaiser Wilhelm Institute and other universities established in Göttingen. So there were three places which were the center of European science type thing. Okay, and so this was the people trained at various institutions. So that is about revising, and then the big quote from Niels Bohr is that if quantum mechanics hasn't profoundly shocked you, you haven't understood yet, because it really makes your mind spin, because some of the words, concepts that we deal with, something called the wave particle duality, which actually challenges our notion of reality as we know it. And then, later on we'll talk about something called uncertainty and tunneling, entanglement, hidden variables. Those concepts are totally alien to our mind of the visible world that we see it. Okay. And now this is, I think I just thought that, but now there were challenge from the traditionalists, because the people who were trained with classical Newtonian physics and to the new so-called Young Turks. And this was the contest that went on in 1927. We talked about something called the Solvay Conference, which was funded by a Belgian industrialist named Solvay. And there were like several Solvay conferences that were held. And the two arguments that went on between the two well-known figures of that time, Niels Bohr and Albert Einstein. Einstein had difficulty accepting the idea that this is quanta, and he, even until he died, he never reconciled with the concept. And this was the thing. So I just.
Is that really necessary? Good Lord. The interference pattern in the fracture. The motion of the wave through the molecular structure. I've been looking at it all wrong. I can't consider the electrons as particles. They move through the graphene as a wave. It's a wave. The moment to applaud would be now.
Okay, so this is, it was popularized in the theory type thing. And this was, I think most, maybe not everybody has seen the second link that I had sent out about the detailed physics thing, because I recorded some more details, because we didn't cover it last time. So, but I'm going to assume not everybody would have watched it, type of thing. So, but this was accidental discovery, again, done by the Bell Laboratories. It's just like, because the patent fight was going on between Western Electric and General Electric, and the two physicists that were employed by the Bell Laboratory, a guy named Davison, spelled with two S, and Germer, and they were, bombarding nickel with electrons. And by this time, and obviously Davison had written in his job contract that yes, he was allowed to do independent research. He did not have to really be responsible. So to their credit, Bell Laboratories had let him do that. Now, and he had also traveled to Europe and heard some of the theoretical physicist lectures that electron can be as a wave, that was given by a French physicist named de Broglie. And so this experiments proved that yes, electron behave like a wave. So that was one of the fundamental experiments that was done thanks to the Bell Laboratory. And again, this just incorporates the smallest particle, which is the electron, and even fragments of that to the stars. So that is where the Bell Laboratory looms large. It's just mind-boggling as to how in the fundamental finding of, we saw the movie, the clip Big Bang and the Big Bang Theory, that again dates back to, we'll talk about in just a few minutes, as to how the two people who were working with the radio antenna discovered and actually proved what came to be known as Big Bang Theory. Okay, and so that was a start of as to how it was discovered. Both of these findings were discovered accidentally, and it's just phenomenal as to how it just came about. The third experiment that particles and electrons have what is known as spin, that was done by guys named Stern and Gerlach. So sometimes even negative experiments can have value. And obviously, a lot of people know about the cosmic microwave background radiation because if you listen to like Hawking's lectures or Neil deGrasse Tyson, that's always, it's well publicized. But this experiment is not as well known. Stern Gerlach, these were two physicists who were working with silver and magnetic behavior of the, electrons in magnetic field. And so that came to be known as a Sturm Gerlach experiment, as to it proved what is known as an inherent property of particles called spin. And this was done in 1922. So this was, there was depression and silver was expensive. And the trivia was that to buy silver, they got funding from one of the founders of Goldman Sachs. So, so that proved, something spin as a property of quantum. So he just proved it on more. And then further, this experiment further modified. And by this time, Gerlach had stayed in Germany, and Stern was a German Jewish person, physicist. He had come to the United States, and he modified the experiment, and Stern eventually got the Nobel Prize during war in 1943. So as usual, wait for 20 years. So those were some of the classical properties. So the quantum particles have varieties of properties, which is like the mass means, that, electrons is weightless, and the spin and charge, energy, and the same time. So this is the comparison between the two big ideas that reconcile. Now, this may sound to most of us like, what does it all mean? How does it affect you? But it's the basis of everything that we see around us, starting from computers to generating electricity to GPS, lasers. So all the, obviously, going to the moon was based on classical Newtonian physics, but the other day-to-day conveniences that we see are all based on this. Now, at the same time, America was making its forays into research, and the old thinking from the European school was something called invisible ether that was all around and that propagated. So and the two scientists now named Michelson. Okay, again, he was a Jewish immigrant on the settled on the West Coast, and this is a fascinating story as to how the country was innocent type of thing, that he was a poor son of Jewish immigrant from California, and obviously didn't have funds to go to college. So with whatever money he had saved, he came to Washington, and Ulysses Grant was the president. So when the president was out on his walk, he met him and appealed him, says, well, the president had certain seats that he could reserve at the Naval Academy, about 10 people. So, and he had already submitted 10 names. So Michelson was disappointed. But then it's finally, when he was going to go back dejected, he got the word from one of the government officials that, President Grant has extended, has broken the law and given an extra scholarship. So he ended up with the Naval Academy, and then subsequently went to University of Chicago and was mentored by other physicists, and proved the speed of light. That the speed of light, in any medium, this based on, this were some clever experiments were done by shining light on various angle mirrors and showing that the speed of light was constant, in all, in both all directions. So that just proved the concept of ether at rest. And considering how far back was that, their measurements for speed of light were remarkably accurate, because it's almost 300,000 kilometers per second. And it's, so even with the modern things, they were remarkably accurate. So it just goes to show that, how wide open United States was, and, and a man without any resources, so it just really just blew my mind out as to how it was that, okay, you could just say, "Hi, Mr. President, I want scholarship." And the same ideas have been extended in the most recent Nobel Prizes, because Albert Einstein had proved that, yes, that based on his general theory, that there's to be something called gravitational waves, the curvature of space-time. Now, before, in his general theory of relativity, it combined the concept of space-time as one type thing, and he had theoretically proposed that there should be something called gravitational waves, so it's bending of and that experiment was proposed by these people, okay, and this is, Kip Thorne had proposed the concept as far back as in 1968, and it took, a long time to get the funding from National Science Foundation and very bearish, and it took, and the initial experiments, were not that successful, but it took almost 30 years, a team of 1,200 physicists working on the team to discover the presence of something called gravitational wave, and the difference that was noted between the two arms. The one was in Louisiana, another was in Hanford, Washington, laser interferometers, and the same concept, which was proposed for determining the speed of light, was utilized, and this was to avoid the disturbance from from various from the Earth's motion and other things. These instruments had to be very precise, and it really took some marvelous amount of engineering. And finally, in 2016, the laser gigantic interferometer, that's what the LIGO stands for, was able to detect a signal from 1.3 billion light years ago of two massive black holes colliding. And so it was a groundbreaking discovery of what Albert Einstein had proposed almost 100 years ago. So it just shows as to how the two were combined. Okay, now I think moving right on, okay, back in the 19th century, a guy named Hertz had discovered what is known as radio waves, that you did not need wiring between the anode and the cathode to detect signal. And he was able to detect a faint signal without any type of wiring, and that turned out to be a radio wave. Now, again, he had he was curious type of thing and had discovered, but he never really thought that to put as a practical view. When he was asked, what is the use of this? He just shrugged and said, no, don't know, don't care, type of thing. But an Italian scientist, not a scientist, I should say, but a scholar perhaps, who used to read everything that he could get his hand on, a guy named Marconi, he saw the radio waves and put, all these ideas to see the practical use as to how to improve wireless telegraphy. Because obviously with the empire, it was very important to improve the communication. And if you did not need cable, that would be a dramatic improvement. And the biggest empire was the British Empire. So he went to the British Post Office and managed to get the patent of this device. And that was the start of wireless telegraphy, i.e. radio. Now, at the same time, a lesser known scientist named Jagdish Chandra Bose had invented some of these similar device, but he, again, so like decided, for whatever reasons, decided not to patent it. Okay, so he was, and then he, all this mad rush of patenting it and trying to make money, just, he said, well, I don't want any part of it. And he just went back to Calcutta and quietly taught students. So this was, so Marconi uses Bose's 1899 invention, okay, to receive the first transatlantic signal. And he was granted patent by the British Postal Office engineers. And Bose's results were published in Royal Society, that extra so this was, the little odd bits of science that may be of interest. Now, again, Now, science was universal, as we talked about at that time, that even though during the war, Germans were enemies, but astronomer of some repute at Cambridge, okay, named Eddington, was sent a copy of this paper by an intermediary. And this is Eddington at a younger age and at an older age when they finally did meet, okay. And they had proposed, and there's a movie about Einstein and Eddington that I did not put the clip, starring David Tennant, who was the doctor, long-standing Doctor Who, okay, the science uh, TV fame, okay, and it was a well-done movie as to how the Royal Society and British established when funded the experiment to go during the eclipse and take picture of the stars as to how the position was shifted based on Einstein's theory. And that expedition was obviously it was hazardous because they had to take glass plate X-rays, and Eddington traveled to the island, Principe Island, and did manage, obviously they had to depend upon the weather and elements. And the two expeditions were sent, one to Brazil, another to coast of Africa. And they were luckily when the clouds dispersed, and they were able to get at least a couple of photographs. And based on precise calculation as to shift in the star position, were able to prove that yes, that there was definitely curvature of space-time. And that just made Einstein the superstar. And these are, you can see the telescopes on the side up here. These are the massive equipment that to transport to the little island and adjust. And during the eclipse, they were able to take, I probably can't see the photographs of the somewhere around the line, there are stars and based on the angular shift. And this was the headline of the New York Times. Lights all askew in the heavens. Agree agog over the results of the Einstein theory triumph. So this was, the dramatic thing that just made him world renowned, and the rest was. And then later on, obviously, he traveled around the world, and he was like the superstar of his age at that time. And then again, obviously, now again, how politics interfered with this thing as years passed around between late 1920s to 30s with the rights of Nazis, that he was considered as well. This was part of it. This was not really Aryan science. So people who had done some pioneer work, a physicist, a lesser well-known named Leonard, okay, they all got on their case yet that this is obviously Jewish science, and that with and it was it contradicts the classical Aryan scientist. It's just almost nauseating to see as to how he was his reputation was maligned and was persecuted. Okay, and again, these are then obviously, as it quite happens, when for Nobel laureates, expertise extends into varieties of area. So this was his, his views, and again, his so-called God letter was one of the most famous letters. Was sold for astronomical sum of $2 million. Okay, so why that is, I guess we all love. Okay, this is, and he was again, went about we're digressing, but was a firm believer in Baruch Spinoza, and and as a young college student, I learned about Baruch Spinoza from reading Jeeves. Okay, so I think those of you who are a fan of P.G. Wodehouse would recognize, and this was one of his pictures as to when he, okay, and this is again, and obviously he was very astute, that if it is proven right, Germans will call me German, the Swiss will call me Swiss, French will call me great scientist. But if it didn't, this was before it was proven. If it was proven wrong, the French will call me Swiss, the Swiss will call me German, the Germans will call me a Jew. Okay. Now again, so obviously his thoughts. Now there were those of you who have already seen the YouTube video that I sent out, I apologize, but he did not have believed that the universe was pretty steady. In some way, he was sort of traditionalist, that believe in the Newtonian concept, and as we already saw that he had hard time accepting the quantum theory, quantum physics as the real McCoy, as he would call it. So he believed in the steady state theory, and based on his own calculations, his mathematics was very good, but not perfect. Okay. And so he had introduced what he came to be to known as cosmological constant. But there are other people who are more mathematically inclined on mathematical physics. Guy that some of you may know, but I assume not everybody does. A Belgian Jesuit priest who had a PhD in physics from MIT. He had proposed that based on his Einstein's own equation, that what he had proposed as the universe being steady based on his general theory, that did not make sense. And he had showed that the universe was actually expanding. And when the two of them met, Einstein had difficulty accepting, George Lemaitre's work, that his mathematics was excellent, but his physics was abominable. So he just never. And at the same time, a lesser known person named Friedman, who was in Russia and had fought in the war for the Russians, had also written letters to Einstein that he had some mathematical error in his field equations of general theory of relativity. And finally, Einstein grudgingly accepted this after visiting what Hubble had proved on based on astronomy. And it took another 70 years for supernova expansion, and this was the most recent Nobel Prize that was awarded by the expanding universe. Okay, and so again, this was proven in 1998 and recognized in 2011. So that's the now, and this was the most famous. I think I'm sure some of you have seen this famous photograph that is colorized, and this is the greatest collection of European and American intellect. Okay, I mean there are about, and you can see from the slides, there are about 15 Nobel laureates, including who is who of chemists and physicists. They're all at the third most famous Solvay conference, and that was a conference which goes down in the history of science as to the argument went back and forth for the 3 or 4 days that the conference was in session between Niels Bohr and Albert Einstein, as to Einstein had could not reconcile with the idea of quantum jumps and quantum basis of light, that the light can be in terms of quanta and type of thing, and can take jump type of thing. He still believed in the classical Newtonian concept of particles as waves, and it goes back to Thomas Young, where the famous double slit experiment that we talked about when we talked about Royal Society. And so it was just, the big this thing, and Bohr was ably assisted by some younger physicists that we'll get to in a minute. On the other hand, just a couple of years later, a brilliant, astronomer par excellence, who was, got his PhD at the University of Chicago and was working at, on the West Coast at the Wilson telescope, and he was, obviously assisted by an able assistant named Westo Slipher, and something called the Cepheid variables, the binary stars. There was a woman named, they were called computers in those days because they looked at the X-ray plates and measured the distance of the stars and the red shift, okay, based on spectroscopic observations. And so Westo Slipher had showed that the galaxies were actually had showed a red shift, means they were moving further and further away. And this was again, with the bigger telescope, Hubble had, proposed that yes, that we were not just living in the Milky Way, but these were actually true galaxies, and they were moving further and further away. So the universe was a lot bigger than we assumed to be. He studied that, so he proved the existence of Andromeda Nebula, which was thought to be just a cloud of light. So that and he resolved that there were individual stars inside this nebula, and also resulted in one of the most dramatic discoveries in cosmology. And again, they were and the stars which change their brightness, the Cepheid variables, is related to from bright to dim again, that takes place. And they were much further away than we thought in Milky Way. So that the Andromeda Nebula, quote unquote, was a galaxy in its own right. So this was the idea that things are a lot bigger than they were assumed in the earlier days. So there was a dramatic discovery, and it took for a while for the knowledge to get dispersed, then
Hey,
at the same
Bharat,
time. Yes, I'm sorry. Go ahead.
hey, I just want to give you a chance to breathe. I have a question about the Big Bang Theory,
Uh-huh.
not the TV show. Is the universe expanding according to the Big Bang Theory infinitely, or will at some point it stop and then start contracting?
Nobody knows, but I think the most my understanding is it will expanding and it will become cold and type thing. So now there is another concept that beyond that it's kind of limits of knowledge type of thing, that there are people who propose something called the multiverse theory. There are more than there are a couple
Right.
of other scientists who have proposed the idea of something called the multiverse, that there may be more than one universes type of thing, and it may contract, but the general thing is that it's expanding, and the rate of expansion is increasing further because the temperature that is there, that is this something called, we'll get to it in just a few minutes, and something called cosmic microwave radiation. It's almost approaching so-called Kelvin limit, because if you to jog your memory, Lord Kelvin had said something called the absolute zero, and the temperature of the cosmic microwave background radiation due to the length of time that it has occurred, called 13 billion years, is almost to 0.4. I'm like, so it's very close to absolute zero. And when you get to the absolute zero, all the motion of the atoms and other stuff stops. So then it will be just a black void. That's my understanding type of thing. If anybody.
So there is a stopping point.
Yes, that's we know. But obviously, that reaches our limits of knowledge, because as to what will happen in future, that's as to whether and that's where even we get down to even with the start of universe, as to something called, you may or may not have heard the word that Stephen Hawking and other people talk about, called, it started with something called the singularity, and all the physics literally breaks down. So we, as a result, we don't have any idea as to what happened at that time before that. So that's our limits of our knowledge, because we don't know the absolute beginning and absolute, what happens at the end. So that's where we are, our reality limits, we reach the limits of our imagination or our measurement, type of thing. And that was one of the problems that Einstein had, because he thought that the beginning of the universe, which starts with what was called as singularity, that the concept that Stephen Hawking had proposed, as to in the beginning there was singularity, that it was like everything was, in like a one point, and that smacked too much of them, as to that George Lemaitre was a clergyman or a religious person, and it goes down to something called the primeval atom. So that smacked Einstein more to the religious basis of it than this thing. So perhaps that may be the conscious or subconscious reason as to why he had difficulty expanding, believing into the Big Bang type of thing. So, but what happens to that? That's just people, it's like, I'll get more into it. I'll have a nice slide that is coming up. If you just give me a few minutes, I'll get to that. Thank you for asking. Okay, so So this was, so he had proposed theoretically that there should be something called where all the space-time collapses and that do exist. But initially, this was hard to prove based on one Oppenheimer, before he got involved into became administrator of the Manhattan Project. This was his work that he had done on astronomy, and this was some of his original papers that, based on mathematical analysis of Einstein's equations and cosmology, it proposed the paper that yes, black holes do exist. And this is, you can just see that how low the temperature is. The cosmic microwave background radiation is almost close to zero, so 2.72 kelvins, okay, type of thing. So this is, and so this is, so Einstein was, you can say, was a reluctant father. And then we'll talk a little bit about, an Indian astronomer. This is called the Chandra Lab, who started out working in Cambridge and had proposed that when stars reach the limit of 1.4 mass of the sun, they would collapse and form something called the black holes. Okay, and interestingly, based on quantum physics, another Indian scientist named Bose, had worked on something called the quantum statistics and had written letters to Einstein proposing that when the subatomic particles cools down, a new state of matter would exist. This is something called the Bose-Einstein condensate, okay, which has different properties. All of us know very well the solids, liquids, and gas. And in the sun, when it's extremely hot, it becomes something known as plasma, which generates the fusion. But when things are cooled down, the matter loses its property and forms something called the Bose-Einstein condensate. And that's based on that. And the elementary particles are divided into two categories: fermions and bosons. Okay, and we'll talk more about Fermi, who was a giant in his own right and had a huge, larger-than-life role in the Manhattan Project. Okay, and this was, a little scientific controversy that brewed back in 1920s when Chandrasekhar, or Chandra as he was called, he was a young postdoc and had presented paper in Cambridge about proposing the black holes. And he was, under the supervision, or was working with Eddington, and Eddington, had attacked his paper that does not make sense. The other astronomers and everybody who was there, knew that this young postdoc was absolutely correct, but nobody actually rose to defend this young postdoc. And obviously, and he got really disheartened type of thing. And the earlier thing was done again by a Russian scientist named Schwarzschild, had proposed something called the Schwarzschild radius of stars. And this was the book that I read a long time ago called Empire of the Stars, the controversy between young Chandrasekhar and Eddington, who was the who is who of astronomy, Astronomer Royal, in Cambridge. And Chandra finally moved on to the United States and worked at what is known as Yerkes Laboratory, which was a telescope in Wisconsin, and worked on the during the Second World War in Maryland as well. And he was an excellent teacher par excellence. He used to travel from Yerkes Laboratories near Madison, Wisconsin to Chicago and taught for several decades. And he was recognized, with the Nobel Prize, several years later. Okay, so that's a little side story on, okay. So everyone had agrees with what the mathematicians call singularity and this radius swipe, and because when the stars get older, they collapse, and the sun would squeak down to like 3 kilometers in size, and all the matter becomes pretty heavy. That 1 gram weighs like millions of tons. So so this was the concept of black holes that came about. Now, at the same time, there were other advances that were taking place, which is the science of crystallography, which is using X-rays to study chemicals. and the father and son duo, named Braggs, had worked on asterocrystallography and had determined crystallography of various elements, starting from sodium, which is a fairly regular this thing, and the crystalline structure of the molecules of sodium and potassium that Bragg and his son had, and they were the who is who of crystallography, and mentored a lot of physical chemists, including Dorothy Hodgkin and Max Peruz. He was a German immigrant, determined the structure of hemoglobin. Okay, so this was the combining, physics and chemistry based on using X-ray tools. And later on, as we talked about, Niels Bohr with the idea of electrons orbiting around the nucleus, which comprises of protons and neutrons. Now, mind you, neutrons were not yet discovered. Okay, and so based on that, he had proposed, that the electrons are orbiting in something called the orbit. And the orbit when the orbit is full, that two electrons, the electron literally jumps. And that was a very alien concept to science at that time. And it took several years of mathematical thinking and experimental work to prove. And obviously, this you may know about in your, in your class, chemistry class, that the orbits have proposed as to the higher orbits have more electrons. And this was, and it goes on as to, it reconciles the periodic table, starting from the lowest element, i.e. hydrogen and helium, to all the way to uranium, as to the varieties of orbits have how many electrons would be in that orbit. And once the orbit gets full, then the electron jumps to the other orbit, so that you cannot accommodate any more electrons. And so this was, really a brilliant way of reconciling three disciplines: mathematics, physics, and chemistry. And this was when Einstein read this was his quote about it: "This is the highest form of musicality in the sphere of thought," as to how brilliant it was. Okay, and this is what this is the slide that I wanted to show you. So how, so this is the Big Bang expansion. So this is something called singularity at the bottom. And when the universe expanded with a Big Bang for first 3 minutes, this massive inflation took place, and the afterglow of light. So, the scientists have worked out the physics up to the early first 3 minutes. That is the book by a guy named Weinberg, who proposed the inflationary expansion of universe and the afterglow, and this has to do with the cosmic expansion. And then it expanded dramatically, type of thing. And when later it started cooling off, the earlier, so-called plasma coalesced and started with the early elements that formed the hydrogen and helium. And it took several million years, and gradually, we went up the whole periodic table, and we went all the way from, hydrogen, helium, to we'll get to about how. And this is the biggest thought that you could see how we talked about the atoms and electrons, and the atom at the smallest possible scale that was, detectable based on tiny cathode ray tubes, to the expansion of the universe. So from the smallest scale, we were able to reconcile. So that literally proves that how Carl Sagan said that you're literally stardust. So that was proven. So that is the fascinating story of human thought, as to how we were able to reconcile the biggest with the smallest. Okay, and the expansion as it continues. Now there are still a lot of things that are unknown, which those of you who are more have studied physics formally would know that
nearly 14 million years ago, expansion started.
So this is, the Big Bang, and we already talked about Gerald Lemaitre, and I already mentioned that earlier, as to how he, really did not find it hard to buy, with Lemaitre. Okay, so this was, the introduction of And we already talked about the cosmological constant. And finally, and this has been put to rest, with more sophisticated astronomical observation. Okay, I'm going to skip this one type thing. Now, at the same time, there are some other mathematical geniuses who work purely on intellectual power. A guy who was more of almost like either we can call it savant or Asperger's, named Paul Dirac. Okay, he put the particle physics and reconciled that with Einstein's theory of relativity. And this was pure mathematical thought that, I'm not even going to try to explain this complex formula, but he was able to reconcile is something called the Dirac equation. So he reconciled the both Einsteinian concept of relativity and quantum physics or quantum mechanics. He was able to unify it while describing motion of an electron traveling at extremely high speed. Okay, so and the idea of he worked on it for almost 2 or 3 years, just simply with paper and pencil. I guess that was before the computer days, and so he was able to reconcile this on a mathematical thought. Now, he a lot of times the mathematical physicist look for something called the beauty of the equations. Okay, and those of you who have studied more math than I have know that is something in mathematics, something is called the Euler's equation. That's called the most beautiful equation in mathematics that reconciles, numbers and geometry together. It's considered the classics of the 19th century, Euler's equation. And the same way, Paul Dirac was looking for the mathematical beauty of reconciling these two different thoughts in science. Okay, and when he looked at it, he was surprised that what he was reconciling the motion of electrons with theory of relativity. But based on that, when he interpreted the equation correctly, he thought there was even more to it than he thought, that there should be a particle which is similar to electron but has a positive charge. So, and that it was surprised that there was something called what you can call a doppelganger of the particles, which would never, he didn't think it was not discovered at that time. But if these two meet, that was called, obviously, if you read science fiction, you realize there's something called antimatter that pilots the Starship Enterprise. Okay, but so this was, based on the mathematical equation, he was able to deduce that there should be a particle which is identical, but with a positive charge, something called positron. Okay, so this was theoretically proposed. Just so happened that just a few years later, a physicist working with something called the cloud chamber on the west coast of US, a guy named Carl Anderson, was studying cosmic rays. Again, this has nothing to do with atomic physics as we know it. Cosmic rays were coming from above, and he was studying this based on simple water vapor with magnet, and he was able to show that there is something called positron, that the particle did travel in different direction. So what he had theoretically proposed was either by sheer coincidence or what have you, it was proven that it did exist. So it just showed the power of the intellectual giant of Paul Dirac. And so, and I'm sure those of you who are engineers or have taken more science, would recognize that there was the intellectual tour de force. Now, at the same time, the quantum scientists were making progress by leaps and bounds, as we talked about the Denison experiment and Niels Bohr and his proteges, i.e. Heisenberg and Schrödinger, where the center of research of quantum science was shifting to Copenhagen. Okay, but at the same time, one of Rutherford's students, Chadwick, had worked on the papers that were done by the Curies, who were again working with radioactivity and bombarding it to beryllium plates, and the particles that were released, that they had thought that they were protons, means heavier, but based, their interpretation left something to be desired. The interpretation was not accurate. And when Rutherford and Chadwick read his paper, that what they were looking at was a particle inside the nucleus, which is neutron. And so that was the starting of discovery. And again, it's an interest. He's a personal human interest story that he became a physicist by mistake. He was enlisting in a class at Cambridge and stood in the wrong line. He wanted to study math, but stood in line for physics. But then he liked the physicists who were his professors and ended up being physicist. And again, during First World War, happened to be in the wrong place at the wrong time, so ended up serving 2 or 3 years in prison as a foreign national. And finally, was proved the existence of neutrons. So the standard model that we know, that we all see during the, I'm sure in the 50s when you grow up, saw the nucleus and the electrons wandering around, which is not actually the true, because the electron, if the nucleus is here, the electron is about 12 miles away. So, but that's the classic diagram that you see for any radioactivity warning. Okay, so I think we're in, and then when the Solvay conference, we'll take 1 or 2 slides and then we'll take a break. Okay, that when one of the young physicists, who was, mathematician and physicist both, and musician as a sidekick, was a mentor by Niels Bohr. And when Niels Bohr and Einstein were going back and forth, Heisenberg, had come up with the idea as to something called the uncertainty principle, that by just the fact of observing these particles, you cannot do both at the same time. Where it is located and what is the speed, you cannot measure that. And that, and again, it's popularized in the Breaking Bad Heisenberg, but that's not the same Heisenberg, but to disappoint you, the TV fans. And that's, and that was the Heisenberg uncertainty principle. And just to reconcile some of these complex math, he and another mathematician named Max Born had proposed something called the matrix mathematics, which is a different concept than the standard arithmetic that we know it. In arithmetic, obviously, when you multiply 3 and 4, no, the sum is same, it doesn't matter the position. But in matrix mathematics, the position of the number makes a difference, that the result is different. So a totally new branch of mathematics called matrix algebra was discovered by Heisenberg and Born. Okay, so we already talked about how, okay, so I think we should take a few minutes break. I will pause the dictation, that monologue, resume recording. I think so. We talked about Heisenberg, and I think he has become the popular culture with the show that we already talked about. So
he was very young when he was awarded the Nobel
yes,
Prize,
he was
right?
like 27.
Barely
Yes.
30, right?
Yeah, he was under 30. Yep, he was 27.
Yeah.
And then, then again, as during the break time we were talking about, he was a very strong nationalist. So unlike a lot of the other people, he did not, leave the Nazi Germany, and was a really patriot. And he was the head person of working for the German atomic project, but they were working on the heavy water. And once the bombarding of the heavy water plant in Norway took place, then they were really, kind of left holding the bag. And there was even the cloak and dagger story, that a baseball player come in Air Force up from a soldier. He was sent to assassinate Heisenberg at a conference in Switzerland. But somewhere along the line, it just never panned out. So it's one of those stories that I had a slide for that, I forget his name, but so he was sent to kill Heisenberg when he was going to be at the meeting. Now, again, so this was the concept of an older scientist. He was 30 something, so he got past his prime. So as we talked about de Broglie's equation, where the electron is a wave, but that just was for only one particle. So Schrodinger took up a challenge, that to combine it for for the entire wave. So reconcile classical physics with no, let me see if I can get the brighter image. Okay, let's see, where did my magnifying lens disappear? Okay. Oh, that's not good. Oops. Yeah, I can't magnify it. So, but I'm sorry, I think I lost my magnifying lens somewhere on the slide. Okay. Oh yeah, it's on the other side. Okay, so now I found it. So this is what, the classical physics. Basically, you all know from high school physics, kinetic theory and potential theory, energy combined. Okay, I think. But so what Schrodinger did was combine this thing and extended it to quantum science. And this was, now don't try to get too much into it, but he took the Greek letter called psi, PSI, and he combined that, with very complex mathematics to show the so-called and combining energy with quantum science. It's something called a wave function. And again, now in spite of that, he, after proposing the equation, which was a groundbreaking finding in theoretical physics, he had some ideas about his own experiment, okay, about his own thought. So to prove that, yes, this was all really hard to imagine, is the most well-known, uh, thing was Schrodinger's cat, which is known to as probably even longer time in science than Heisenberg uncertainty. Okay, and he proposed the so-called a cat is alive or living. Okay, as a cat is inside a radioactive, jar, which the hammer would strike and the radiation would disperse and the cat would die. And from the outside, you could not tell from the experiment whether the cat is alive or dead until you make observation. So, and that the analogy is extended to the particle, that the particle, as the electron, is a wave or a particle, that until you make the act of observation, it doesn't decide. So it kind of makes up its own mind as it goes along. So this was the classical thought experiment, which Einstein was famous for, but this was the Schrodinger's thought experiment to concerned with the act of observation changes. And in quantum physics, the act of measurement has a huge impact. Oh, Moberg, yeah, thank you, Karen. Yeah, that was the name that I couldn't come up with, so thank you for that. Okay, I'm sorry, minimize that. Okay, so this was Schrodinger's experiment. Now again, he was exiled from Nazi Germany and had thought about various other places to work, including to faraway India, but ended up with the invitation of the Irish leader, De Valera in Ireland, and had extended his thought as to how the origin of life, can be explained based on the basics of physics and chemistry. So the book that some of you may, but the biologists would definitely know, it's something called the What is Life? And this was a book that he thought about how the life could have evolved based on physical and chemical basis. He proposed what we knew from the 30s as gene, as he described as aperiodic crystal, and how the life could have originated based on from deep sea, and the concept called What is Life. This book influenced a number of physicists, including the famous James Watson, to change their careers from physics to biology. And that inspired the start of what we now know as molecular biology. Okay, and now, and so that was a huge impact, larger than life. And the book is considered very small book. Obviously this was just varieties of thought. He had not done any experiments, but that influenced a lot of people to change careers. At the same time, Italians, not as prominent. Rome was not as big a center, but had, were some very smart people who were again victimized by the rise of fascism. And the giant of that time, was Enrico Fermi, who was from a young age, who was an experimental physicist, worked on the same mode as Rutherford and Chadwick, and worked on particle physics. and had come up with the concept of neutrons, which based on their energy had come up with the varieties of new concepts, had worked on something known as beta decay as to how the, we talked about the alpha and beta decay. Alpha was the helium particles, and the electrons was something called the beta decay type thing, and which is later on now considered as a weak force. We'll talk more about it a little later on. I may have some more slides on it about the forces. Obviously, all of us know the gravity is a force, the same way as something called the strong force, the weak force. And so this is the concept, something called the electromagnetic radiation is known as something called the weak force. And so Fermi had done a lot of the original work on it, and he was awarded Nobel Prize in 1938. And then later on, his wife was Jewish, so obviously he made ways from Copenhagen to University of Chicago, and he was probably one of the few well-rounded physicists, not just theoreticians, but also experimental physicists par excellence. And you can say that he was, along with Einstein, who was who at that time was at Princeton, another wandering scientist who had come up with the idea of nuclear fission named Leo Szilard. Okay, and those 2 or 3 people were instrumental in writing a letter to FDR about the US atomic project, i.e. Manhattan Project. So, and Szilard and Fermi had done the original experiments of trying to see how much uranium it would take to sustain what is known as chain reaction, because the elements, the heavier elements, have spontaneous radioactivity, and based on the isotopes of uranium, it can sustain a chain reaction and releasing energy based on Einsteinian formula. Okay, and so they were calculating how much uranium it would take, and some of the earlier calculations were done by Leo Szilard and Enrico Fermi. And after the Manhattan Project started going, okay, and again, to digress, the original idea that was done was in February of 1919 by a guy named Otto Hahn, who was again working with neutron bombardment of radioactive elements, and had managed to split the nucleus, but was unable to interpret the result because he was not a physicist, by training, and had uranium was split into beryllium and krypton. So the 2 fission products were released, and these results were sent to a woman who was not did not get the Nobel Prize, but he was his assistant, Austrian by ancestry, and had to leave Nazi Germany, and was in Copenhagen. And when she got the results from Otto Hahn, who was they were co-workers in Berlin, and based on that, she communicated the idea to Niels Bohr, and later on the idea was shared with the Brits and Americans. And when the paper was published earlier, that again, one can say that was the theoretical or practical start of Manhattan Project. And this boils down to the final statement that you may recall from the movie Oppenheimer: "I have become death, the destroyer." And this is based on the Hindu epic Bhagavad Gita. And I'm not going to try to pronounce the Sanskrit words, but I think I can. I still remember enough of my high school Sanskrit to say this is not a literal translation. The translation is very awkward. "Time I am the word destruction, causing powerful to destroy earth have come, without excluding the event that do not exist, those who are in opposite rank of warriors." So that's what the literal translation is. But this was paraphrased in the final statement by Oppenheimer, who was a student of Sanskrit, as "I have become death after seeing the Manhattan Project." Okay, so I'm sorry. So Lisa Meitner was, she did not want anything to do with it. She was nominated for Nobel Prize, but for whatever reasons, either because she was a woman or because she was Jewish, but she was not done experimental physics, so she was never recognized as. Now, if we talked about the chain reaction, and so Fermi and Szilard had calculated the amount, and they carried out the experiment in the soccer field at University of Chicago. And because as the chain reaction is sustained, the energy that is released and the neutrons can be slowed down by graphite, which is the huge rods of piles of graphite. And so they were able to set up the experiment, which was an effort during the wartime. Took 45,000 pure graphite blocks weighing about 350 tons, and inside that it was fueled by the uranium rods, which are, you can see on the slide here. Okay, I'm sorry, that the horizontal ones, there are the right here. And as the rods were inserted, as the radioactivity was released, and the was slowed down by the graphite blocks, and when the counter showed that there was enough radiation, the rods were pulled back. Now, obviously, they did not know for sure that whether they will be able to stop the reaction. There was at least some theoretical possibility that whole of Chicago could go up in the smoke type of thing. But Fermi's theoretical calculation and as the practical confidence were strong enough that yes, this was the chain reaction was sustained, and that gives the green signal to scale up the production of radioactive material to form the nuclear bomb. Now, and then obviously it was necessary to produce a radioactive element, and this was the start of the so-called big science. And this was undertaken on the West Coast by an experimental physicist named Ernest Lawrence. All of you recognize the name of Lawrence Livermore Laboratory, which is still very much active in the production of atomic weapons for US. And Lawrence was, experimentalist par excellence, and at the same time he was a savvy politician, was able to raise funds that were needed for these huge particle accelerators. Particle accelerators were, speeding up the electrons under electrical field or magnetic field, and those were discovered, by the so-called splitting of atom was discovered by the British scientist named Cockcroft and Walcott in Cambridge. But those were small and like a tabletop experiment of only 4 inches of diameter. And to increase the speed of particles traveling in a linear fashion or in a circular fashion needed bigger and bigger investment of millions of dollars. And Lawrence was savvy enough that he was able to raise the funds. And the cleverness that was there was a lot of the radioactive elements that were discovered had medical uses as well. Because as you may recognize, since the start of X-rays were used for medical purposes, i.e. for radiotherapy for cancer. And the same way isotopes were useful in treatment of cancer. And that opened up a lot of the checkbooks. And obviously, once the Manhattan Project was funded, the funding increased exponentially. And Lawrence was able to build bigger and bigger cyclotrons from just few inches to as much as 90-inch cyclotrons in Lawrence on the West Coast. And again, they were hasty. They were great experimentalists, but were in too much of a hurry to interpret results. And Kevin put that the Curies were the Nobel royalty, so to speak, that Marie Curie's and Pierre Curie's daughter, Irene and Joliet Curie, were at a Curie Institute. And as early as 1935, they were able to create radioactivity and had created artificial elements. Now, at that time, some of the people from Britain were warning them that do not publish these results in Journal Things, but they had gone ahead and published the results. So the findings were available to anybody who was able to interpret it and use it, including the Germans. Okay, so the moratorium finally started out a little later than should have been, perhaps, and so the whole knowledge was very widespread. So this was the impetus of Lawrence's laboratory had actually seen the results at the same time of artificial radioactive elements, with higher and higher atomic number could be created, but they were unable to interpret the results, so they kind of missed the boat on science. So, okay. Now, on the same time, from the small scale, we'll go up to the bigger scale type of thing. That this was the most remarkable findings as to how, and at the same time, the cosmologists or astronomers were trying to interpret, the spectroscopic findings from stellar observation. And now the thoughts were going on between so-called, Big Bang expansion. At the same time, there are other school of astronomers who thought that the universe was a steady state. Okay, and there were some reputable members, and the one who is well known to the British, is a guy named Fred Hoyle, and who was not a believer in universal expansion because it was not proven, type of thing that they. So they believed in the so-called steady state theory in spite of Hubble's findings. Okay, and as a tongue-in-cheek, he had on one of the BBC announcers, he coined the word Big Bang, and it stuck. But at the same time, to his credit, Fred Hoyle was an original thinker. When he was traveling on the West Coast, he had suggested to astronomers named Fowler and Baden, okay, to look for signature of elements in the stars. Okay, so based in astronomical and spectroscopic observation, they were able to detect the spectroscopic signatures of heavier elements into the stellar observation. So now, and so the atomic number and the atomic orbit of the elements coincided with the observation of the stars. So this actually, and it turns out all the elements were formed in the beginning of, shortly after the Big Bang, when now it turns out that the most abundant element in the universe is iron, because the iron nucleus 56 is quite stable because the energy is balanced between the so-called neutrons that are orbiting around the iron. So beyond that, the further elements are formed in a different manner in the stellar thing. So that's why the iron 56 is the most stable element. And this graph coincided very normally with the star formation. So that just proved finally the so-called formation of synthesis of elements in the stars. And later on, and then obviously, the Fowler and others recognized this was the paper that was published in the 50s, but somewhere along the line, Fowler was recognized as a Nobel laureate, and Fred Hoyle was left alone. Okay. And now at the same time, we talked about the Big Bang expansion. We talked about it showed that the two astronomers, Penzias and Wilson, were working with Bell Laboratories, and they were trying to amplify the signal for the telephone transmission. And they kept detecting what is known as a hum from all around the universe. And they were unable to interpret the results. At the same time, some of the theoretical cosmologists at Princeton were trying to interpret the results and to understand what they were detecting when Penzias and Wilson talked to the theoretical cosmologist at Princeton named Dickey. They said, okay, well, they had discovered what we were theoretically proposing. And as it happens quite often, Penzias and Wilson were recognized as a Nobel laureates. And it took almost 50 years for Nobel Committee to recognize James Peeble, who was one of the theoretical cosmologists, to get the Nobel Prize in 2019. So delayed Nobel, so it helps to avoid death. So James Peeble.
Right, I think you know the story about how they thought that the inside of the radio telescope, they thought that birds had defecated on it, and that was what was causing.
Yeah, they cleaned.
So they had this team that went out and cleaned the thing minutely, and it was
Yes,
obviously still there.
that the birds were eliminated. Yes, yeah, thank you for sharing that. Yeah, so they were not able, they were engineers primarily, I think, I don't know I've forgotten their background, but they were not able to interpret the results. And prior to that, there were some other people who were more of a theoreticians. There was a crazy, a kind of a polymath Russian named George Gamow. George Gamow was a character. He was, he spoke with strong Russian accent, was exiled from the Stalin era, and was not just an astronomer, but was also a biologist. And George Gamow had a huge role to play in interpreting the so-called DNA code. So they were all, physicists by say, but they dabbled in biology. So says, well, the code should be. So he had written a letter to Crick and Watson that what the code for all the amino acids should be. They'd never done any biological work, but he was, he'd come up with the mathematical concept as to how these amino acids, which are essential amino acids, could be interpreted. So he was kind of a polymath to his own extent, and they had something called the RNA tie club as to how, the Watson and Crick principle as to how the proteins could be formed, as to say, okay, you'll pick this amino acid and this is this thing that you would work out on this theoretical basis as to how certain amino acid form. So that's a interesting story of molecular biology that was proposed by a guy called George Gamow. And he had proposed a paper, he had written a paper called Gamow, Alpert, Herman, and alpha, beta, gamma paper. So that was one of the starts of the Big Bang Theory type of thing. So there are a lot of other people who were involved in this thing. So it's an interesting how the intellectual this thing was going on. And again, this just amazes as to how long people have to wait to be recognized by the Nobel. So we talked about James Peeble, and there was another guy who had discovered neutrinos. He waited for almost 40 years. The man named Ruska, who had discovered the electron microscope, okay, and he waited only for 54 years. So I think finally when they run out of this thing, and so it just, it's an interesting scientific, dilemma. Okay, and now another, if you had to make 2 or 3 people, along with Albert Einstein, okay, have to be a man who, now after the Manhattan Project ended, Richard Feynman, who is a figure larger than life, a lot of you know a lot more about him than I do, type of thing, that, he was young and brash and was marched to a different drum type of thing. And again, and after that, they were trying to, after the Manhattan Project was finished, they all went back to the universities and were trying to combine these 2 disciplines of special theory of relativity and particle physics. They were trying to reconcile these 2 ideas. And Feynman had tried to explain that the quantum science was even more weird than we thought. When particles combine, they borrow energy from future, and after they annihilate, the energy is returned. And this was something called the photon is released and is absorbed, that thing. So this was the start, and he had explained that based on, had simplified a lot of these, there were hundreds of particles that were discovered in particle accelerators. So try to make sense out of these particles, he had come up with the concept of something called the Feynman diagrams. And again, when a conference was scheduled in after the war in 1948 at Shatter Island, and then later on in the Poconos. And in the Poconos, Feynman presented his concept of Feynman diagrams. But again, a lot of the traditional scientists were obviously aghast that this is some young guy who's proposing these ideas that just did not make sense. And he was told, says, well, you're talking nonsense, you should sit down. But luckily for this thing, another equally prolific mathematician scientist named Julian Schwinger had worked out the complex mathematics of reconciling the quantum equations with general relativity and put them on a strong mathematical basis. So these both ideas were presented in the Poconos conference. And that was the birth of the most reliable theory in modern physics, that known as quantum electrodynamics. And this is accurate how electrons affect each other and reconcile with energy equation and with electromagnetism and the special theory of relativity. This is accurate to the 1 part in 10 billion. So what has been proven based on experimental basis and was calculated based on a theoretical basis, it reconciles with the accuracy of 2.002319304. So you can find this type of accuracy is almost unbelievable type of thing. So some of these ideas are very hard to fathom or to get your mind around it. That what we consider a vacuum is not full, but it's just, energy is being created. It's almost like you can just say this goes back to the Zen idea of yin and yang. Particles are being created and destroyed in something called in the void, something called the quantum foam, and it's reconciled. So this was explained based on the Feynman diagrams, which is a more easy way to appealing to the eye and easily understand compared to the strong mathematics that was proposed by Julian Schwinger. And at the same time, Oppenheimer, who was was instrumental in organizing conference, had received papers from a Japanese scientist named Tomonaga, who had also come up with the same concept of mathematical equations of combining these two big giant processes. So all these three people were the founders of the quantum electrodynamics. So they can say this is one of the most intellectual achievement of modern science. And so this was the picture from 1947 of Linus Pauling. Okay, and let me see if I can. Okay, sorry, I have to move this. And Edward Teller, who was the father of the hydrogen bomb, and becomes sort of the dark hero of Oppenheimer, because he gave evidence against Oppenheimer, saying that Dr. Oppenheimer should be denied the security clearance, and he became the persona non grata among the physics community. Okay, and so these are varieties of people, and then you can see that that's all male crowd, as was the case, and it still is to some extent in physics. So this was the start of the reconciling these two ideas. Okay. And this is a rather elaborate slide, but I think I don't know, some of you saw the YouTube video might have seen this. Atoms to Higgs, this is the so-called standard model of science. Okay, and you can just see the smallest building blocks of matter. Okay, starting from matter made of atoms to electrons, protons, and it goes down. Now this is further goes down to, this comes down to the concept of quarks that came up later on, which we'll talk about later. Okay, and again, by this time, scientists had discovered so many particles in accelerators in Chicago and Stanford and the other areas that they were totally flummoxed to became known as what is known as a particle zoo. Okay. Oops, sorry. I'm trying to magnify this without much success, Yeah, sorry, I think I can't find my magnifying lens here. Okay, so particles in a zoo. So we'll talk a little about the guy who came up with the concept of quarks, that all these particles had to make sense on a mathematical basis. And so even the protons and neutrons, they stay together, they are combined with something known as a strong force. Okay, so even the things are even smaller compared to electrons and protons, and which came to be known as quarks. And it is combined that the proton is composed of 3 quarks, the up and down quarks that makes the proton, and they have something called the electrical charge, and when it combines, it forms the proton. And the neutron is made of 3 other quarks, which are even smaller particles than proton and neutron are, And so that was the concept of something called a strong force. That's why they stay in the center and the electrons orbit around. So in the universe, most of the things are made of three things: up and down quarks and electrons. Everything else is, gravy, so to speak, and just exits a lot of in the lab. So, and now all these particles are massless. So they need some type of other force to keep it together. So that's why the other particles are proposed something called the bosons. Okay. And now, as we said, that the particles are massless, and they obtain their mass, or the weight is done with something called the Higgs boson. So the search continued for 50 years for something called the Higgs boson that was theoretically proposed in the 60s. Okay. And now the concept of quarks was, again, with all these particles, came sense because another prodigy who was a contemporary of Feynman, when, again, just like Rutherford and Bohr, they're totally different people. Again, Murray Gell-Mann was a Jewish person who grew up in New York and wanted to be an archaeologist, but his father said, become an engineer. Engineering he was klutzy, so decided physics is the thing. He was disappointed that he didn't get scholarship at Harvard or Princeton, but settled for a lesser school called MIT. And then obviously got his PhD earlier and was instrumental in working with the particle, making sense out of particle physics. Now, he was well versed in other Eastern philosophies and trying to make sense out of this. He had created a model to explain the so-called particle zoo. So based on the Buddhist concept of eightfold pathway, had created a model of quarks. Now originally they were not called quarks, but again, he was listening to Finian's rainbow and came up with the name quarks. Originally they were called partones by Richard Feynman when they were trying to make sense out of it. Okay, and later on, he worked with the freestanding institute called Santa Fe Institute, and again, was a giant in his own ways. And so from the fields to the boson, so mass is resistance to motion. Okay, and this is the energy equation that we all know. And so how particles acquire mass requires existence of a new field. Okay, and field is something that you call, it's not like a field for growing wheat and rice, but a field is the electromagnetic field, as you can just visualize from the magnetic concept. And so by interacting with this field, as like, for example, you're trying to walk through molasses, you will feel resistance. So you require weight. Okay, so that's the concept of getting mass with motion. And that's what the idea of a boson that came about. And the Higgs boson was proposed, so it took almost 50 years for the boson that was theoretically proposed by various other scientists, including Peter Higgs, and it took 50 years for the Higgs boson to be proven at the CERN Particle Accelerator Laboratory at CERN, Switzerland. Okay, and what does it all mean in real life? What are the benefits? The benefits of this are all around us, the radios, TVs, computers, World Wide Web, GPS, medical imaging, X-rays, CT scanning. Now, some of the more interesting research that I wasn't aware of is there is something called, obviously, all of us know the CAT scanning, okay, but there is also something called the spectral imaging of spectroscopic X-ray imaging. So you can just see these X-rays are generally black and white, but this is the spectral images that shows this dramatical details of human anatomy. Now, all of you have, are familiar with, you may have heard about, a PET scanning or PET treatment, which is the positron, which we talked about earlier, that is used for imaging, which is an expensive way to get the exquisite details of biological tissue. The same way that in US, mostly we use PET scanning or proton therapy, but in Europe, that is known as a hadron therapy, means very localized radiation therapy with carbon energy is used for cancer. The same way, so this is the depth of tissue is very precise, and you can deliver a lethal dose to cancer. and this thing that so proton beam therapy, that is the big way of treating malignancy. So it does have a lot of practical uses as well. Okay, and again, the basic principles of science were called nuclear medicine. We already talked about the magnetism and the spin that goes back to the Stern-Gerlach experiment. So the nuclear medicine, was proposed as far back as 1952. That was proved on medical use by several decades later, and by a guy named Lauterbauer and Mansfield, and there was the start of MRI. Because all of us, human body is 80% water, and water is hydrogen atoms. And when it is subjected to large magnetic field, the hydrogen molecules spin in one direction. And when the magnet is spilled, it goes back to the original position. So based on various mathematical calculations, very complex mathematics, imaging is generated, and that is the magnetic resonance imaging. And the original idea were proposed by a guy named Damodian in 1971. As to why he was ignored for Nobel Prize, that is still left in the secrecy in Sweden. Okay. So these varieties of methods were proposed by this thing. So and that to the chagrin of Dr. Damodian, he was given the patent for this, but still his work was neglected. At the same time, again, Bell Laboratory figures large in the discovery of transistor. Transducer and resistors, two words are combined to form what is known as a transistor. And again, they were trying to amplify the signal for telephone for the Bell Laboratories, and based on certain elements which have a different conductivity, they came up with the original concept of transducer. And this was shown, at the Bell Laboratories in 1950s. And that was the start of the, later on came to be known as a semiconductor revolution. Okay, and again, there's certain varieties of personalities. Shockley, who was not the nicest person to work with, and moved on to the West Coast and started some founding companies of the early days of Silicon Valley. And again, very few people were able to work with him. And again, and he was off the target, was involved in so-called genius sperm factory that we talked about in science. And again, and the technology was put on more solid basis by an engineer who worked for Texas Instrument named Jack Kilby. He simplified the transistor of manufacturing, and formed the, and there was a start of the semiconductor industry, and Jack Kilby was recognized for his invention back 50 years later. And so that was the start of the Texas Instruments integrated circuit manufacturing process. And this was again more formalized by a guy named Noyce, who was the founder of Intel. So that was the big start of the various elements. They initially had used germanium. Later on, Noyce used it to silicon, and that was the start of the computer industry on the West Coast. Okay, and John Bardeen, continued to do remarkable work, and after he resigned from Bell Laboratories, had moved to the University of Illinois, and had worked in something called the condensed matter physics, as to how the behavior of elements changes at extremely low temperatures. And the idea was known since 1910, but was primarily pressed on something called the Cooper pairs, as to how the electrons behave at a low temperature. And that was his work, which was recognized for. He was one of the few persons got the second Nobel Prize. And again, the computer industry and the quantum science comes big into day-to-day use of the charge coupling device, the digital cameras that we use, and all the imaging that is used for radio telescope and astronomy, that is based on digital imaging with semiconductor industry. So this again goes down to, back into the 60s, and the ideas based on photoelectric effect. And so the basic science is being used for practical uses, that we all use it without giving it a second thought. Now, again, continued with the saga of the exiles from Nazi Germany. An Italian-American scientist named Emilio Segre was, when he had visited the Lawrence Livermore laboratory, he would given a sample of molybdenum, okay, and based on that and the molybdenum atom, he was able to detect radioactivity and see that the element transferred to a new element, which is the first synthetically generated element. The Greek word for this is artificial, okay, and that was called technetium. And one of the isotopes of technetium-43 is technetium-99, which is the workhorse of nuclear medicine. If you've ever had brain scan in the old days, or liver scan, or thyroid scan, that is like the working isotope called technetium-99. And unfortunately, Lawrence, who was a better politician than a scientist, was when he saw Emilio Sagre had to run away from Rome and could not go back, obviously, and so he was confined to California. So he reduced his salary. For a well-respected physicist per se, he was initially offered like $300, and Lawrence reduced his salary to $150 or something. And again, he continued to work for the Manhattan Project, was kind of the unofficial or official photographer of the Manhattan Project. So a lot of the documentation was done. And then he continued to work on varieties of other elements, and had later on, after war, had discovered varieties of other new elements, synthesized. And again, we talked about the positron earlier, and then later on, the search was on for diagnosing for discovering something called the counterparticles of proton. Okay, and he was instrumental in discovering something later known to be antiproton. So again, the benefit of Nazi Germany was similarly another woman who was again exiled from Nazi Germany had created a more formal model of the Bohr's atomic project, of how the electron orbits occurred, starting from hydrogen to lithium and so on higher and higher. And you can just see how the chemists would understand that thing. And this was a woman who was again, was a physical chemist of his own right, was not hired at Johns Hopkins while her husband was working, given the excuse that this would be smack of nepotism, and she was given some low-lying jobs. Eventually, she moved to San Diego and had a job. And when she won the Nobel Prize, this was the announcement in one of the San Diego newspapers: San Diego mother wins the Nobel Prize. Okay, so it was an interesting thing as to how people were recognized for their, biology rather than. And again, this narrows down to the end of physics, as we talked about the Higgs project, and it took some, 50 plus years for, you can see from 1950s, the idea of CERN, the Particle Accelerator Laboratory, which is on the border of Switzerland and France, the CERN laboratory, and it took, a lot of work of thousands of scientists to discover, what is known as the Higgs particle. And this is Peter Higgs, and the other scientist who had proposed the idea, was Francois Engelbert. So there was a Nobel Prize in 2013 and so that put part of, Finn on the standard model of physics of particles. And still, if it hadn't been discovered, the whole idea would have gone up in air. And the more recent Nobel Prize, which was where we talked about the black holes earlier, the concept goes back to the 30s, and the ideas were proposed, on a theoretical basis by Stephen Hawking and Roger Penrose, who are more known mathematicians, that proposed the concept of singularity that I alluded to earlier. And it took, various astronomical work by astronomer named Andrea Gans and Genzel, working with infrared telescopes, and finally, based on the, they were able to actually detect the presence of black holes, and astronomically. So this was reported in 2018, and obviously, so finally, black holes' existence was proven. Okay. And Now, again, the concept of switching back to electrons, the electron behavior is a lot more weird than you realize, that we already talked about the wave particle duality, that they could be waves or particles depending upon when you observe. Another property which is weird is called tanglement. And I would strongly recommend, I'll send out the link by Jim Al-Khalali about the quantum word, this thing. So, and they've done some excellent documentaries. It will take about 40 minutes of your time. But Jim Khalali explains the weirdness of quantum physics, which is entanglement, means a particle would change the position. For example, he gives the analogy of spinning a coin on its edge, whether it's going to end up with heads or tail. And if there are two particles, they have like a strange communication. If one lands on head, the other would automatically switch to tail. So that's called entanglement property. Again, it was a weird concept which was very hard for anybody with common sense to accept, but it has been proven. And this was, and BBC has done an excellent documentary. This was proposed in the jazz era. So they had created a whole musical song just to explain the idea of entanglement, because this was proposed in the jazz era. So there was one of the clips that they had said called entanglement. And again, other weird properties that are associated with quantum science is called tunneling project. It's like all of a sudden the information is communicated with something called quantum tunneling that figures large in in quantum computers, and radioactive decay, and in the stellar fusion in the sun also. So these varieties of figures, and still this did not make sense, because people still said that the whole theoretical Copenhagen interpretation was not complete, because there were still certain puzzles that were unsolved. And finally, people decided just to throw up their hand that, okay, we are not going to worry about it. As long as it works, we won't explain all the weirdness that we see of changing in position and entanglement. Okay, and the physicists finally just, back until in the late 60s, they just threw up their hand and gave the idea, says, well, just shut up and calculate, basically. So as long as it works, don't try to explain all the theoretical basis. And this was questioned by an Irish physicist named John Bell. He proposed something called the local variables. Now again, with the coin or like a ball, you could see the color that would change. What Einstein has proposed, that when he challenged the ideology, he had proposed something called the Einstein-Poisson EPR paradox. It says, well, this was already predetermined. For example, that gives the analogy of a glove, that the glove is inside the box. One glove is left-handed. You automatically know that the other has got to be right-handed, okay, when two gloves are hidden. So there is something that is already pre-existing property of a particle that is there. So that's called the local reality. And so this is something called, and this ideology was questioned by John Bell. And this was carried out by the younger generation of physicists later on, who were more into Eastern philosophy of Zen. And some of you may have read the book called The Tao of Physics, okay, type thing, as to, incorporating various other philosophical bases and physics together. And now quantum entanglement was actually proven by a guy named John Clauser, who worked in the hippie era on the West Coast and had proposed various experiments, to prove the so-called quantum entanglement, as to how, if you look at the position of one particle, it would automatically change at a distance. The position would change. So these clever experiments were devised, and it took almost 30 or 40 years, for this to be proven, based on various particles and shining laser beams on calcium crystals and changing the position dramatically. And a lot of people thought that these experiments, even Richard Feynman did not believe that this would work. This whole ideology was nonsense as to how spooky action at a distance would work. But Alan Aspect, who was a French experimental physicist had devised this experiment of shining polarized light on calcium crystals, changing the electrical facility and as to how the polarity would change. And that showed how the quantum entanglement was proven. And this was the most recent Nobel Prize given in physics in 2012 for quantum entanglement. And again, it happens out, that Clauser is, again, he's not a meteorologist or type thing, but again, he's a big name in so-called climate change denier. Okay, so this goes to show that. Okay, all right. So again, and so the quantum entanglement was one of the big, and the most recent Nobel Prize was something called the femtosecond. Okay, and I'll just see if I can show the video of that. Nope, I don't think it will play. Oh yeah, it will play.
In 2023, researchers Pierre Agostini, Ferenc Krauss, and Anne Levine clinched the Nobel Prize in Physics for pioneering work with attosecond-long light flashes, revolutionizing electron study. Imagine capturing Quicksilver's supersonic speed on film or Batman's chase. You'd need ultra-fast shutter speeds. Similarly, to observe atomic processes, these physicists developed incredibly pre-flight bursts. What's an attosecond? It represents 10 to 18, which is a decimal point followed by 17 zeros and a 1. To grasp its brevity, consider this. There are as many attoseconds in a second as seconds in the universe's age. So why the buzz? These fleeting pulses can unveil unknown physical phenomena in materials. They might usher in ultra-fast electronics through ultra-fast switching. Moreover, in medicine, attosecond science offers promise. By flashing a rapid light pulse on a blood sample, molecular changes become detectable, potentially revolutionizing diagnostics, including cancer detection.
Okay, I think we should stop share, and so we're done with the physics part of it, type of thing, and I will record the chemistry part, and and I'll see if we can, let me know as to what day you would want to do the extra session type of thing, because I think I'll be glad to do the extra session type of thing. So I think, you can just let me know as to. Yes, thank you, Kevin. Penzias just died this month type thing. So yeah, that was the obituary I read that type thing. So okay, I will stop the share. Sorry, and okay, and then we'll and I'll also record some of these and send it out type of thing. So you can, if you have interest in time,